Mass spectrometry is a really important chemical technique in so much of analytical chemistry these days, be it environmental, medical, geological, straight up chemistry, material science. You need to know what something is made of, and the composition of certain elements is going to make a big difference to your findings. So being able to understand how mass spectrometry works, and especially the calculation at the end, really important. What we're going to focus on here is just, you've got different isotopes of a single element, work out its relative atomic mass, kind of the most basic ones of these calculations you can do. And we're going to go through the 4 different types of calculation one by one. So first one, working out the relative atomic mass of something. So we know that our equation is AR equals mass 1 times abundance 1 plus mass 2 times abundance 2 plus mass 3 times abundance 3, so on, or depending how many masses or abundances you got, divided by the sum of all the abundances. So that's going to be the only equation we're going to use, and we're just going to have to use it in a few different ways. So on this question, we simply want to work out the mass, or the relative atomic mass. They've given us all the isotopes, they've given us all the abundances. All the questions I've used here are from the tasks in the question pack. If you look at the past paper questions, you need to be able to work out what is the exam question asking you for, so which of the examples I'm going to go through does it match up with. And that's one of the skills you need to develop. That's why I'm not going through the past paper questions with you here. So our AR, which is what we're trying to work out, is going to equal mass 1, and the M/Z ratio is 70 of our first one, times the abundance, 20.5. And then we're going to add on our second mass, which is 72, times the abundance, 27.4. And we're just going to keep on going until we've done all of the different abundances with all the different masses relating to them based on this graph. They could give you the data in words, or they could give it you as a graph. There's examples of both in the past paper questions. You need to be able to do both of them, so it's worth having a go at them all. And then we need to divide it by the sum of the abundances. This one's going to be easy because they've given you percentage data, and percentages will always add up to 100. So then you just need to type in that top row into your calculator, include the brackets, otherwise your calculator is going to get confused. And you're going to end up with 720, or 7,263.2 divided by 100. So your AR is going to equal 72.6. 32 if you really want to go. Now, you can always check whether that answer makes sense. 72.6, is that between the 70 and the 75? So they're the 2 extreme masses you've got on the graph. Because relative atomic mass is kind of an average mass, it has to be within those 2 extremes. 72.6 is almost smack bang in the middle of that. So that makes sense. If you've got a number which is a bit higher or a bit lower than the 2 extremes, you've probably just done something wrong in your working out. Maybe you've accidentally pressed times instead of a plus when you're doing the calculation, or you haven't included the brackets, or you've forgotten to times by 100, something like that. But always check, does your answer make sense? Is it within the range of the isotopes in the question? So if this one, is it between 70 and 75? If it's not, have a go at doing it again. You probably just made a mistake typing it into your calculator. It's probably not that you've done bad chemistry. Now, they can make this type of question harder by talking about ratios, and this is becoming more and more common, but actually, if anything, it's even easier. So we're still going to use the same equation, and we're going to be talking about the oxygen isotope and the abundance. How do you spell abundance, is it? We've got 2 different isotopes, 16 and 18 in this question. We don't have the abundance of either of them, but we're still trying to work out a relative atomic mass. So it's still one of the ones where we just have to put it into the equation, no rearranging. They've told us that oxygen 18 has an abundance 9 times less than oxygen 18. Oh, that doesn't make sense, does it? We're going to change that to 9 times less than oxygen 16. Now the question's correct. So as soon as they say something is 9 times less or 9 times greater than the other, or 2 times less, 2.3, 3 times less, anything like that, to keep things simple for you, put the smallest one having an abundance of 1. And oxygen 18 has an abundance 9 times less than 16. So we'll just say oxygen 18 has an abundance of 1. And now oxygen 16 has an abundance 9 times bigger than that. What number is 9 times bigger than 1? Well, that's 9. Hopefully you can do 9 times 1 by now. And now you've got every bit of information in the table. You can just plug it into the equation. So mass 1 is 16 times abundance 1, which is 9, plus mass 2, 18, times abundance 2, which is 1. And divide this by the sum of the abundances. This time you haven't got it equaling 100. 9 plus 1 is just going to equal 10. And then you come up with 162 divided by 10. So your AR is going to be 16.2. It tells you 3 significant figures, so you leave it like that. So if anything is 9 times bigger than another one, or a certain number of times bigger than another one, just put the smallest one equal to 1, and then the other number is however many times bigger it is. Now we're going to get to the trickier ones. So they could give you a question where they actually give you the relative atomic mass, and this time they have. They've told us the relative atomic mass is 84. We want to now have to, we're now going to have to work out something else. And in this time, we're going to have to work out one of the M/Z ratios. So first thing I would do is put this in a table. I'd always use a table. I'm just going to call it ABU for abundance now, because I can't work out good abbreviation for abundance. Our isotopes they've given us, 82, 83, 84. They told us they are the first 3, so we know this missing one is going to come after them. We'll call it X for now. And the relative abundances are going to be 2, 2, 10, and 3. So put it into the table. That makes it clear that you've got all the information from the question. And if you put it in the table, you should be able to work out what's the thing we haven't done here. Oh, that's right, this one, they haven't given us one of the isotopes. This is the type of question we're looking for. Then just put it into the equation. So AR, they've given us it. It's 84.0. It's going to equal mass 1 times abundance 1, so 82 times 2. Then carry on going through the table. Whatever's in the top row, times it by the number directly below. Add it to the third row and third column along, 84 times 10. And on this last one, we don't know the M/Z ratio, so we don't know which isotope it is, but we do know the abundance, so you can still times them together. We just call that 3x. Don't forget that we still have to divide it by the sum of the abundances, so just add these up. 10 plus 3, 13, plus 2 plus 2 is going to be 17. And then once you've written that, that'll be your first mark. Now you can do a bit of rearranging. So we're still going to have 84.0 times everything in the brackets and add them together. 1170 plus 3x divided by the 17 times both sides by 17. Now you can take away the 1170 from both sides, which gives you 258. That's the value for 3x's. We just want 1x, so divide both sides by 3. And that gives you 86. So our missing M/Z ratio must be 86, and it should always be really close to a whole number. So 86.01, 85.1, 99, something like that. If you've got 86.4 or 85.6, you're miles away from a whole number. You've probably gone wrong. Go back to your calculation again. So just to help you with the rearranging, that step we've times by 17 for some of the abundances. There we've taken away the 1,170 from both sides. On this step we've divided by 3. That's how you always do these questions. Set it out like that, you shouldn't be able to go wrong. Always draw the table out to keep it fresh in your mind about what you're actually doing. Sometimes they'll also miss out one of the abundances, but they'll always do that in the percentage, and you know the percentages have to add up to 100, so that might be another first step they could add in if they want to. Final type of question they could ask you, and these are probably the hardest. So this one's all about phosphorus. This data is obviously all made up. Phosphorus is pretty much only really has one stable isotope, 31, but the whole point of these calculations is that it's not going to match what the periodic table says, because you've got a sample which is different. Well, the periodic table gives you samples averaged across a massive range. You're just looking at a single sample. So first thing to do, draw out the table, see what information we've actually got. So we're going to have phosphorus isotopes. We've got 28, 29 and 35. And they've given us the abundance of 35. That's a 50. And they haven't given us 28 or 29. And we don't like it when we've got two unknowns in a question. That just makes things difficult. So let's just call it X and Y for now. So we can see that phosphorus 35 makes up 50%. So we're dealing with a percentage. That means all the abundances, X plus Y plus 50, must equal 100, because that's how percentages work. So X plus Y therefore must equal 50. We're just taking 50 away from both sides. So we can say that Y equals 50 minus X. And then we can now get rid of the Y in our table, because we've just said here that Y equals 50 minus X. So rather than writing Y, we just write 50 minus X. Writing down that step there, that would get you the first mark on this question. Now, they've also given us the relative atomic mass, 31.8. So let's stick it in the equation that we've used every time so far. So 35 times 50 will be our first one, because they're the whole number, or they're the actual numbers we've got. They're the easiest. Then, with our next one, 28, the abundance for that is just X. So we'll just call that 28X. We don't really know what else to do with it. And the third one, our for our mass, 29. And our abundance is 50 minus X. Don't forget that we have to divide by the sum of the abundances. We've said that it's going to equal 100 because they're percentages. So we've got to that stage. Now we need to do the rearranging. So times both sides by 100 and undo everything in the brackets. So 31.8 times 100 is going to be 3,180. Then we just need to undo what's in the brackets. 35 times 50. 28x we can't do anything with, so we'll just leave that at that. We've got 29 times 50, which is 1450, and then 29 times minus x becomes minus 29x. So we've times by 100 and times out of the brackets. So we've got this. Now we just need to get all the whole numbers, so the 1750 and the 1450, onto the left-hand side. So just subtract both of them. That's going to give you minus 20 equals 28x. Take away 29x. And then 8x is take away 29x gives you minus x. So minus x equals 20, or x equals 20. And at this point, even though you've drawn out the table and it should be quite clear to the examiner what's going on, I would always write 20. I'd write down the symbol of the isotope and just say its abundance, 20x. You haven't finished yet, because it also wants to know the abundance of 29. but the abundance of 29 is going to equal 50 take away X, which was the 20, which equals 30%. And 50 plus 20 plus 30, that equals 100. You've probably done it by, they seem like sensible numbers that will give you something in the middle. They're the only types of calculations they can do for relative atomic mass calculations.